Okay, welcome everyone. My name's Simon Salomon. I have no special role apart from being a speaker, but I have the pleasure, I've been asked first of all to introduce Paolo Piccione as a member of the organising committee.
Thank you very much. Thank you, Simon. Good morning, everybody. As someone said, I'm Paolo Piccione, and I'm, in fact, representing the Brazilian Mathematical Society. I'm a member of the directory board of the society, and I'm here to welcome all speakers and participants to this fantastic event about special holonomy and geometric structures on complex manifolds. The Brazilian mathematical community is very dynamic and very engaged in research and organizes this kind of meetings very often in several institutions in the country, especially here at IMPA, which is the excellence center of the Brazilian mathematics. But this particular event, in my opinion, really shines in our panorama because of the area and also because of the massive participation of renowned specialists in the world. And I feel I'm entitled to say this because I'm a differential geometer myself, so I'm fully aware of the work that many of the speakers have done in the area. So I'm particularly proud to be here to welcome you. And this event was made possible by the work of the organizing committee, which includes senior researchers, but especially younger researchers who have really done an excellent job in organizing on this. And I want to thank them personally. Simon Chiossi is one of them, so please let's. And Viviana Del Barco, please. And Andrew Clarke. These are the people who really worked for this meeting. And finally, I would like to thank all the sponsors. There's many sponsors for this event. I hope I don't forget anybody. In fact, I'm using my phone to make sure that I have a complete list. First of all, the Institute, the IMPA, who provided financial source, the FAPERJ, the state agency of the state of Rio de Janeiro, the CAPES, national agency, and the Simons Foundation. I think Robert will tell us something about it. The International Mathematical Union and the ICTP also. So we welcome, we gratefully acknowledge the financial support of all these things. And finally, to conclude, I want to say that Brazil is an excellent place for making mathematics and making friends also. So my wish is that at the end of the conference, everybody goes back home with a stronger mathematical background and also with an enriched network of new friends. So long everybody, and I will see you around at the talks.
Okay, so I also have the pleasure of introducing our first speaker, Robert Bryant, who's going to talk. Well, first of all, I should say that when the organisers invited Robert to speak, I don't think they fully realised that he'd come with a whole team of people from the Simons collaboration, but it's great that that's worked out, and the programme looks to be fantastic. So Robert's going to, I see you've added in geometry, but anyway, Robert's going to talk about a century of holonomy in geometry.
Is it on? Can you hear me? Right, okay. Well, thank you, Simon. Thank you, Paolo. It's a great pleasure to be here, an honor to be invited to speak. As you might know, I and a group of friends who've been working in this area for quite a while have been for the last 8 years supported by the Simons Foundation, who was kind enough to fund us as a collaboration for, like I said, for the last 8 years, and also to supply funding for this conference. We're delighted to be here and grateful to have this opportunity. I think it's particularly something that Jim Simons, who was the founder of the Simons Foundation, would have been pleased to be here or to hear about, because in fact one of his first major works was in the theory of holonomy, and I'll mention that a little later on in the talk. I'm assuming that there are several geometers here who are not familiar with the story of special holonomy, and so I wanted to give a talk that was an introduction to the subject. So those of you who have been involved for the last 8 years in the collaboration can probably get up and leave now. I'm probably not going to say anything you don't already know, but I hope that this will set a tone for a dialogue and communication with people who are working in various different areas in geometry. I wanted to talk about a century of holonomy in geometry, because it has been almost exactly a century now since the idea of holonomy was introduced in geometry by the great Cartan. And so I'm going to sort of survey that development and the more recent developments that those of us here in the room have been involved in. Yeah, so this is the advance. Yes, so I'm going to start with a little bit about very historical background. The differential geometry, Riemannian geometry in particular, got its start with this famous job talk, actually, for Riemann, who was competing to be a student of Gauss, who was competing to be to get the privilege of being able to give lectures that the students would pay for if they thought they were worth it. And he gave this talk as part of his job talk on the hypotheses that lie at the foundations of geometry. And of course, that's when he introduced what we now call Riemannian geometry, which paved the way for a lot of new mathematics that we'll talk about. But it took a while for the Riemannian geometry to really catch on and people to start understanding what the underlying principles were. Levi-Civita in 1917 showed that a Riemannian metric defines the notion of parallel transport. That is, along any curve, whoops, I think I hit the wrong button. Oh yeah, this button. Along any curve in the manifold, you can define a connection between the tangent spaces along the tangent spaces of the endpoint that gives an isometry between the two tangent spaces. As anybody who's studied Riemannian geometry knows, that it actually depends on the curve. It's not just the endpoints. So depending on how the curve moves, you'll get different identifications between the isometries. In particular, if you take any loop, set of loops based at a point, it gives you a map from the tangent space to itself that's in fact an orthogonal transformation. Whoops. What's happened? Oh, whoops. Oh, there it is. Yeah. In fact, an orthogonal transformation, so you get a set of rotations, possibly reflections as well, depending on the loops based at a particular point in the manifold. Since he noticed that there was actually, that this actually was a group of linear transformations, because you can compose two paths, you'll get the product of the rotations, he got a subgroup of the orthogonal transformations, and the dimension of that subgroup he called the degree of freedom of the metric. And in fact, it's not hard to show, even then it wasn't hard to show that if the dimension of H was 0, that is, that this was only discrete transformations, then in fact the metric had to be flat. But it was not clear what the possible set of rotations you could get were. I mean, in sort of standard examples like the sphere or hyperbolic space, you can easily see that this rotation gives you everything, well, the special orthogonal group, because they're simply connected. But In the hyperbolic case, you can actually get orientation reversing things. Let's see. He knew that it was a subgroup of the rotation group, but he didn't know much more than that. It was Cartan in 1926, just under 100 years ago, who recognized the fundamental importance of this group, the holonomy, which he called the holonomy group of G. And of course, it was only known up to isomorphism, but as a subgroup of the orthogonal group. But Cartan was, of course, immediately interested and curious about what the possible rotation groups could be. And because there aren't very many subgroups of rotations in 3 dimensions, it's easy to just list those, and you can easily see that the only possibilities are all possible rotations or rotations about a single axis, in which case the metric splits as a product. That was easy to show. But the first sort of non-trivial case where you can get a subgroup that doesn't fix any plane but is a proper subgroup was in dimension 4. And Cartan, he showed that if the rotations fix a splitting of the tangent space, then it's locally a product metric, so the problem reduces to product structures. But the first non-trivial case where you didn't get a product metric was dimension 4, where you could have the 4-dimensional orthogonal group contains this subgroup SU2 that preserves that doesn't preserve any splitting, acts irreducibly on the tangent space. And the natural question is there a metric with that property? And Cartan showed that it actually does exist by writing down I started to tell you how he knew, but in fact we don't know how he knew. He just, in his first book on Riemannian geometry, he just says this is true. He doesn't give any indication of a proof at all, or why you should believe it. Sorry?
Did he say anything about?
No. There was no known connection with complex geometry at that point, right? But the first sort of non-trivial group was this SU2, and first the smallest irreducible case, and it's a system of PDE on the manifold. He understood how you could express it as a system of PDE on the manifold, and it's a set of overdetermined PDE. It's degenerate in the sense that, of course, it's invariant under the diffeomorphism group, so standard techniques didn't really apply. But he had, by that time, early in the 20th century, had already developed a theory of PDE that was capable of handling things like this. And he actually he applied that machine. I mean, I conjecture that he applied that machine because after stating this result, he never mentions this result again in the rest of his papers. But he gives the right answer. He says, let's see, I think I put this in the slide. I didn't say it, but I'll say it now. Up to diffeomorphism, it turns out that the set of such metrics depends on 2 functions of 3 variables. And that is, essentially, you get to specify 2 functions of 3 variables on some hypersurface. And then there's a unique way of thickening that. Back up here. There's a unique way of thickening that 3-dimensional manifold to a 4-manifold and extending the metric up to diffeomorphism unique so that you get a metric with holonomy SU2. It's, he remarks that it's nowadays what we call self-dual. He remarks that it's Ricci flat. He remarks all these things about the solutions, but he doesn't give any indication of the proof. However, if you're familiar with the earlier work of Cartan, you can guess what he would have tried to do. And I'm not going to spend the time because I have to cover a lot of ground today. But this theory of exterior differential systems, there's a sort of an algorithm that you can apply once you understand how to set up the problem, and it's immediately apparent when you sit down to do the calculation that run this algorithm, and in a few lines you can prove this result. So he probably didn't think it was significant, or that interesting, because it's an easy calculation. According to him, anybody could have done it, but nobody did at that point. There seems to be very little recognition that this holonomy problem is interesting at that point. But he did raise the problem of classifying what the possible holonomy groups are. And at this time in 1926, he didn't solve it, but he used the ideas to, well, I'll say a little bit more about that in a minute. The person who first looked at the unitary group, the full unitary group, was J.A. Schouten and his student, David Danzig. In 1929, they published this paper on unitary geometry. And they investigated the case UN. And they wrote down what we would consider to be all the standard structure equations and curvature identities and so forth for unitary geometry. They didn't give it a name. And it didn't really catch on until Kahler, in his paper in 1933, wrote a definitive treatise on the subject of what we now call Kahler geometry. That is, metrics that whose holonomy is a subgroup of UN. And it was Kahler who recognized its importance in algebraic geometry and complex geometry, because he explicitly noted that the natural metric, the Fubini-Studi metric, which had been defined years before, that the Fubini-Studi metric had holonomy UN.
Did Kahler actually ever point out that his so-called Kahler metrics have special holonomy? Because he just sort of says, let's consider a metric as defined by potential.
That's right. Yeah. Well, but it's in the papers that I've seen, he doesn't make a big deal about holonomy. He just talks about the fact that there's a parallel complex structure.
If I'm not mistaken, Berger was the person who really emphasized the link between these.
That could be. Yeah. Right. Like I said, it didn't turn up. The direct study of holonomy didn't take off at this point, because the interesting case, I mean, people immediately focused on the connections with complex geometry, and it became a major industry studying that. But certainly Schouten and Van Danzig recognized that this was the case of a metric where there was a parallel complex structure. Or I should say almost complex structure, because at that time we didn't have the Nylander-Nirenberg theorem. And just knowing that there's a parallel almost complex structure doesn't immediately tell you that it's integrable. I mean, that wasn't known until the 50s with Nylander-Nirenberg. And in fact, when you read the literature, people talk about pseudo-complex structures or some word that connotes a not quite really complex structure. And certainly Cartan didn't mention anything about complex structures in his SU2 case, because there was at that time no understood connection between that and complex geometry. Anyway, the subject became named after Kahler because of his work. And nowadays we say a Kahler manifold is a triple. It's a Riemannian metric where there's a complex structure that's orthogonal and varying under the parallel transport of G. In other words, J is parallel with respect to the Levi-Civita connection. And of course, that implies that the holonomy is conjugate to a subgroup of UN. And in fact, conversely, if the holonomy is conjugate to a subgroup of UN, then there's a parallel complex structure, parallel orthogonal complex structure for the metric. And there's in particular, that means that the split of the complex forms. The complex forms split into PQ forms, that is forms that have P that are the wedge product of P complex linear one forms and Q anti-complex linear one forms. You get this nice decomposition, and the beautiful thing is that, and the thing that makes everything useful and important, is that in fact the Laplacian defined with respect to the metric commutes with this decomposition. So on a compact Kähler manifold, you have this beautiful decomposition of the metric of the cohomology groups into this, into a 2-index cohomology group, so the so-called Hodge diamond that turns out to underlie, an enormous amount of the utility of and beauty of complex geometry. Well, I should say, one thing I skipped here is that also in 1926, there was one particularly dramatic and important development by Cartan, in that Cartan used the concept of holonomy to revisit his classification of the real simple Lie groups and the so-called symmetric spaces. And his identification of the symmetric spaces, the classification of symmetric spaces with locally symmetric spaces with holonomy, and it redid this very complicated classification he'd done in 1913 and simplified it dramatically. So the classification of the real types was really the first big result that came out of understanding holonomy. In 1957, Chern considered this generalization of Kähler geometry, where he went back to the notion of holonomy groups. Let's see, I always forget. That's going to go, nope. Yeah, he went back to the notion of what you can get out of a general holonomy group, and he looked at the case where you take any subgroup of the orthogonal group, if H is conjugate to a subgroup K, that leaves a decomposition of the exterior algebra into irreducibles. What he showed was that in complete generality, the G Laplacian commutes with the decomposition of differential forms into K types, generalizing the PQ decomposition in Kähler geometry. And so what you get for a compact manifold, if there were any, that have holonomy K, conjugate to K, is you get this decomposition of the cohomology groups of M into a sum of generalizing the Hodge diamond into these irreducible pieces that come from the irreducible representation of the exterior algebra on Rn. But aside from a few simple examples, this is in 1957, Chern didn't actually look at other applications of this decomposition. He looked at some simple examples like local product structures and locally symmetric spaces, but because at that time he didn't have any other examples to talk about.
Did you talk about the Lefschetz theorems in this context? Because of course the previous
Right.
broken up further.
Yeah, he actually doesn't. He doesn't say explicit. I mean, he mentions the Lefschetz theorem in Kähler geometry, of course, as a special thing, but he doesn't talk about the more subtle things that happen in the case of special holonomy, right? Partly because he didn't have a lot of other examples in mind. And in fact, at that point, he says it's not clear what other interesting examples there are. But in fact, there was already at that time, 3 years earlier, Berger had made progress on Cartan's holonomy problem. He actually he wrote down what he did was write down a set of conditions that were on the curvature, generalizing the Kähler identities, that would be true if the if the holonomy were reduced to some subgroup K, and then he just went through the representation theory and crossed out all the irreducibly acting groups that didn't satisfy these conditions. That there could be non-trivial, there could be non-parallel metrics. Non-parallel curvature tensors. And it's a representation theory problem. You just go through roots and weights and you list every possible representation of compact groups that act irreducibly. And because that classification had been done by Cartan, he could just use that classification, sort of cipher out the. I don't want to trivialize it because it's actually a very difficult calculation. There's several things that take long pages to actually figure out what the possible curvature tensors are. But he came up with a list of all the possibilities for holonomy for things that were not locally symmetric. And like I said, the locally symmetric metrics had been classified by Cartan already in 1926 using this concept of holonomy. So you only needed to consider the things that weren't locally symmetric. And of course, Cartan knew that his SU2 example was not locally symmetric because it would have shown up in his classification if it had been. And the list that Berger gave here in the Riemannian case, he actually did the pseudo-Riemannian case and the affine case and things like that. It's quite a long paper. But the list that he came up with for the possible holonomy groups was this. And I'll just say, of course, the generic metric has, you get every possible rotation. The UM case was known at that time. That's Kähler geometry. The SUM case was, Cartan had claimed the existence of SU2, and it's not hard to, as we'll see, what happens in the higher dimensions. The other dimensions, the other SPM, SPM, SP1, and then those were the sort of things that happened in sort of, you would say, in general dimensions. And then there were three exceptions. In dimension 7, there was this, the first of the compact simple groups, G2, sitting in SO7. In dimension 8, spin 7, sitting in SO8. And dimension 16, there was spin 9, sitting in SO16. And these were and what I want to emphasize is that these were the things that were not crossed off the list because they didn't satisfy the necessary conditions. And so that was the possible list at that time. However, in 1968, Alexievsky actually looked more closely at the 16-dimensional case, did a few more calculations, and showed that, in fact, spin 9 can only occur for locally symmetric spaces. So the spin 9 case, which does, in fact, occur, again, in the exceptional case of F4 mod spin 9, the Octonian plane, that's, essentially it and its dual are the only things that could have holonomy spin 9. Right, so that deserves to be taken off the list, and it was. And this modified list is what resulted. And this was known in 1968. And moreover, it turns out that just like in Kähler geometry, there's an analog of the Kähler geometry story in that the thing that characterizes UM is the existence of a parallel 2 form, that is a 1-1 form, the 2 form associated to the almost complex structure. And you can go through now and see that all of these things are connected to, all of the special holonomies are connected to the existence of parallel forms. In the case of SUM, there's the Kähler form, but there's also a holomorphic volume form, an M0 form that's parallel. In hyperkähler case, it turns out that there are 4 there are three parallel anti-commuting almost complex structures, orthogonal almost complex structures, and they give rise to a three-dimensional space of two forms that are parallel with respect to the metric. SPM SP1, the way you can think of that is the group that, not the group that preserves the IJK, but preserves them up to an orthogonal rotation in IJ and K. So in particular, omega I squared plus omega J squared plus omega K squared is invariant. And in fact, that defines this, this group, SPM, SP1, now called quaternion-Kahler. Then these other two turned out to have, as this was discovered by Bonan, that G2 is defined by a parallel 3 form and it's dual, and spin 7 is defined by a parallel 4 form in the 8-dimensional case, or would be defined. At that time, of course, they didn't know that these things actually existed. The higher dimensional case, I mean, these other cases, as known as far as existing, were this exists. The quaternion-Kahler case exists as a locally symmetric metric, the quaternion projective spaces, but the others don't occur in locally symmetric cases. This one, called Calabi-Yau, is called such for let's see. Because I'll say a little bit about that here. Make sure I get the, okay. So the local existence of these metrics with holonomy SUM, now in dimension m greater than or equal to 2, was conjectured by Calabi. Calabi recognized fairly early that in fact the SUM case could be written down in complex geometry as a single PDE, a single determined elliptic partial differential equation for the Kähler potential. And so the existence of solutions was obvious. It was an elliptic PDE. You could, so there was no, there was no subtle thing. Once you had the complex structure laid out, you just needed a parallel volume form, and that was Calabi figured out that exists locally, and raised the conjecture about whether or not, under what conditions you could actually get a compact Riemannian manifold with that holonomy. And of course, this was a famous result of Yau, that there is in fact you have in fact if you have a Kähler manifold with a non-zero holomorphic volume form, then you can find a parallel holomorphic volume form, and thereby reduce the metric to holonomy SUM. That was a conjecture of Calabi, and Yau proved it. This turned out to have lots of implications in algebraic and differential geometry, and for from the 70s up until for maybe 15 years, this was in some sense the most exciting development in the story. There were lots of applications in algebraic geometry, connections with the theory of calibrations, which we now call special Lagrangian geometry. In the SUM case, formulation of supersymmetric field theories, the discovery of mirror symmetry. You're going to hear a lot about this in other talks, so I'm not going to spend a lot of time on that. But that was the big advance, and it turned out, although I don't have much time to cover it, it turned out that once you crack the SUM case, there's algebraic geometry can help take over and construct compact examples with SPM in higher dimensions. Beauville and others showed that you could actually, if you had a compact manifold with a holomorphic symplectic form, then that implies there's a holomorphic volume form. If it's Kähler, if it's Kähler, then Yau's theorem shows you that you'll actually be able to get something parallel there, and because it's Ricci flat, that the Bachner identities will tell you that the 2 form has to be parallel, and that produces the SPM. So it's an algebraic geometry question to actually find holomorphic compact Kähler manifolds, and that there are several constructions. I don't have time to discuss that, but I think various people will talk about this in the succeeding lectures. I actually want to concentrate on the exceptional cases because in some sense it goes all the way back to Cartan and then goes forward into the present day. After Berger's work, several people, including Alexievsky, Bonan, who I mentioned, who saw the connection with 3 forms, Fernandez and Gray showed that many of the features of Calabi-Yau metrics would have analogs in G2 and spin 7 holonomy, if there were such metrics. And so, for example, as Cartan already pointed out in the SU2 case, they would be Ricci flat. They would. He didn't talk about parallel spinor fields, but that in fact turns out to be the case in this case. And there's an analog, for example, the G2 analog of PQ type decomposition in Kähler geometry happens for G2 in the sense that in G2 you get if V is a 7-dimensional vector space where G2 is acting, then, and you look at the components of the exterior algebra, then the degree of exterior algebra, then each one of them breaks up into a finite sum of irreducible vector spaces under G2. For example, because G2 acts irreducibly on the 7-dimensional vector space, the lambda 1 V, which is isomorphic to V, is just irreducible. There's only one component there. But lambda 2 V, of course, has to have the Lie algebra of G2 in it, which is 14-dimensional, and that leaves only a 7-dimensional vector space. And it's easy to see that it can't have any 0. And what's left has to be isomorphic to the standard 7-dimensional representation, because G2 has only one 7-dimensional representation. In fact, that representation shows up in every one of the non-trivial degrees. The G2 shows up in the lambda 2 and the dual lambda 5. And in lambda 3, there's the 3 form that Bonan noticed, and it's dual. There's also the V's, and what's left over turns out to be the traceless quadratic forms on the vector space. So this is the analog of the Hodge diamond in the G2 case. And there's also an analogous Hodge rectangle for spin 7. But for purposes of illustration, I'm going to concentrate on the G2 case. The spin 7 story is parallel in many ways, although it has its own difficulties, which you'll hear about, I imagine. And in the last 40 years, there's been a lot of interest in this case, the 2 exceptional cases, and a number of breakthroughs. And my involvement in the story actually came in 1984 when I was studying the work of Harvey and Lawson on calibrated geometry, where because it turns out this 3 form, when there is a metric with a parallel 3 form like this in 7 dimensions, it gives rise to interesting calibrated geometries, and Harvey and Lawson, in their famous paper on calibrated geometry, raised the question about whether or not there really existed anything other than the flat example. Because it still wasn't known in that case. And I was lucky. There was, in the sense that apparently nobody had thought to apply Cartan's ideas to actually do this case. And so I sat down to, to try my hand at that. And at that time, I didn't know enough representation theory. I kind of did everything by hand. And the calculations involved doing row reductions of 35 by 42 matrix, which fortunately there was still a lot of big computer paper around, computer printer paper around, and I could write out this 35 by 42 matrix on a big sheet of paper and use a pencil to do the row reductions. And the calculation came out that yes, this thing satisfied Cartan's conditions, it was involutive, and so the metrics had to exist. I had to do that row reduction several times before I believed it. And then, of course, once I knew, I could look for a more comprehensible comprehensible proof. And and it was only after I got the comprehensible proof for G2 that I tried the spin 7 case, which would have been worse by hand. And I didn't have to do that, fortunately. So the existence was, the local existence was settled. It turns out that, of course, because these things are Ricci flat, they're real analytic, so Cartan's methods actually are justified here. And for example, the G2 metrics depend locally on 6 functions of 6 variables. Basically, you have to choose 6 functions on a hypersurface, and there's a unique way to extend off that hypersurface to get a metric with holonomy G2. Holonomy contained in G2. And in spin 7, it's 12 functions of 7 variables, it turns out. So the local generality exists, and once you knew there was local generality, you could actually sit down and try and write out an example. And it wasn't hard to construct incomplete examples. A few years later, Simon Solomon and I actually constructed some complete explicit cohomogeneity 1 examples of 7 manifolds and 8 manifolds with the desired holonomy. So we had complete examples around. And they were basically modeled on Calabi's construction of a metric on the cotangent bundle of CPM with holonomy SPM. You look for something that's a vector bundle with a cohomogeneity 1 action, because they can't be homogeneous. That's not hard to show. But cohomogeneity 1 works. And then at that time, it was purely, I would say, mathematical interest in the subject. I wasn't aware of the relation with M theory or anything like that, but I started getting papers from physicists talking about D brains and P brains and things like that, which I didn't understand at all. But I soon learned what they were doing, or something of what they were doing, and the interest in these in supersymmetric theories in high energy physics stimulated a lot of interest in actually understanding the geometry of these things. And it was in the mid-90s that Dominic Joyce, who unfortunately couldn't be here, was part of our collaboration, but couldn't be here, who developed techniques that I'll say a few, if I have time, I'll say a few things about, that allowed him to prove the existence of compact examples, 7 manifolds with holonomy G2 and 8 manifolds with holonomy spin 7. And, and it was a real tour de force, both imagination and the PDE involved at the time. Dominic was, I would have thought that it was beyond reach at that moment, but Dominic really made a tremendous advance that opened the field, as you'll hear a lot about the geometry of these things in the talks. And so, Dominic, I want to say it's the analog of Yau's solution of the Calabi conjecture, but in fact, that is in the sense that he showed that if you got sufficiently close to and I'll say more about what sufficiently close is, to getting a metric with holonomy G2, then you could perturb it to actually get something that had holonomy G2. Right. But it's not the true analog in the sense that it's not a necessary and sufficient condition. It's a necessary condition, but we don't actually know necessary and sufficient conditions for when a 7 manifold admits a metric with holonomy G2. And of course, this has led to an enormous amount of developments in studying moduli spaces and enumerative problems, which turn out to be very much more subtle than the enumerative problems that arise in algebraic geometry. And we'll hear more about that in later lectures. And since this is an introductory talk, I don't want to spend too much time on that. I just want to give you the basic facts. So I'm going to talk about G2 structures and metrics on 7 manifolds. And as I said, the story for spin 7 is analogous. And here's some of the basic results that we know. If you start with a 7-dimensional vector space over R, first there's linear algebra, right? And a 3-form on the 7-dimensional vector space is said to be definite if when you take the interior product with any non-zero vector and square it, that'll give you a 4-form, wedge it with phi, that's now a 7-form, if that's non-zero for all non-zero v. That's the notion of definite. And if you let lambda 3 plus be the set of definite forms on V, it's not obvious that it's not empty, but you just write down one example, you can see that it's not empty. And it's not hard to show that's an open set, and the general linear group on V acts transitively on this open set. The stabilizer is a compact group, which turns out to be isomorphic to G2. It's compact, simple, and dimension 14. And on V, because G phi is compact, it fixes a quadratic form. And because this is non-zero for all non-zero V, that means that it definitely chooses one side in the 7 forms. And so there's an orientation for which this is always greater than or equal to 0. And in fact, that shows that if you have a connected smooth 7 manifold, and you let omega 3 plus denote the set of everywhere definite 3 forms, that defines what we call the G2 structures on them. And every G2 structure has a canonical metric associated with it, namely this metric that gives the form square norm 7 and orientation that way, with this form being greater than or equal to 0. It's not hard to show topologically that because G2 is simply connected, it turns out that the only way this set can be non-empty is if the manifold is both orientable and spinnable. And if a metric has holonomy G2, holonomy in G2, then there's a G parallel 3 form. There's at least one. And if sigma is, given a 3 form in the thing, if it's G phi parallel, where G phi is the metric associated to sigma, and there are no G parallel 1 forms, G sigma parallel 1 forms, then the holonomy is all of G2. These are things that follow pretty much directly from the structure equations. And finally, in fact, that connection is the connection with parallelism suggests what the differential equation is that you should be looking at. Oh, I'll give the wrong thing. Yeah, that is, if you have a G2 structure that is parallel with respect to its natural metric, then it's closed and it's co-closed, where this sub star means the orientation, the Hodge star operator associated to the metric G phi and the orientation. And And if M is compact and simply connected, and sigma is in fact G sigma parallel, then the holonomy is all of G2. This is a consequence of the Bachner identity. It says that because it's Ricci flat, if it's simply connected, that means H1 is trivial and H1 corresponds to the parallel one forms, and there aren't any, so the holonomy has to be all of G2. And so let me go back to the, as sort of a guide and motivation, the connections with physics and the theory of the complex cases, SUM and hyperkähler. We know a lot about the kind of questions to ask in the complex cases, and so, for example, what can you say about the topology of examples that are complete or compact? What are the moduli spaces? What sorts of construction techniques are available? How effective are they? What kind of singularities can arise? What features of examples will be important for applications in string theory and M theory? What aspects of gauge theory and enumerative invariance can be generalized to the exceptional cases? And are there analogs of mirror symmetry and or the SYZ conjecture in these geometries? I'll just say a few words about the topological properties, things we know now. Let's see, I'm supposed to be 50 minutes talk, right? Okay, right. So, right. Basic facts about the compact things with holonomy G2. If pi1 is finite, the first Betti number is 0. And the third Betti number is positive because there's a parallel 3 form, which is therefore harmonic. The first Pontryagin class can't be 0. In fact, if the first Pontryagin class does vanish, it has to be flat if the holonomy is a subgroup of G2. And it's not a product. You can prove it can't be a product. There's a quadratic form on the second de Rham cohomology class, which you get by taking the cohomology class, squaring it, wedge with phi, and integrating. That's negative definite on the second de Rham cohomology. There's the marked moduli space, that is the G2 metrics with, the G2 structures that are closed and closed divided by the diffeomorphisms homotopic to the identity is actually a smooth manifold of dimension B3. This is the analog of the Torelli theorem in complex geometry. And this Torelli map that maps the diffeomorphism class of sigma to its de Rham cohomology class actually immerses the marked moduli space into this vector space, the 3-dimensional de Rham cohomology of M, with an open image. So we know a lot about the local structure, but the focus on the 3 form has turned out to be really important, and the way we actually understand it is here's the basic idea of Dominic Joyce was that if you take a closed G2 structure that is by some measure almost co-closed, that is the dual of the 3 form, the 4 form has sufficiently small norm in some sense, and some conditions about injectivity radius and so forth. Dominic was actually able to show that if you're close to being co-closed, you can actually perturb it to get something that's actually co-closed as well. A closed form, you actually get it co-closed as well. And in that way, constructing examples that met these close conditions showed that there's a lot of G2 structures. And now, using that idea and looking at these topological constructions that get you close, we now know that there are billions of 7 manifolds that have holonomy G2. Compact 7 manifolds that have holonomy G2. And you'll hear something about that in the later lectures. And it turns out that there are more invariants than just the invariant that you get from the Torelli map. We now know that there are examples. Of that there are invariants that you can construct using eta invariants to distinguish or refined eta invariants that show that in fact this space of the moduli space can be disconnected. You can have two things that have the same de Rham cohomology class that aren't connected to each other. All these, the understanding the full moduli space is still very much an unsolved problem. We know a lot about things that are close to constructible, but we don't know what happens sort of in the interior of the moduli space. When you're close to singular limits, we understand a lot, but that's still a very, very small piece of what needs to be understood. I'll just close by mentioning one idea that has turned out to be that may give an alternative method at some point for constructing examples to methods based on Joyce's construction. If you take this is the analog in G2 geometry of the Ricci flow in Hamilton's program for understanding the Poincare conjecture. For a compact 7 manifold, if you look at a de Rham cohomology class and you look at the set of G2 structures that are closed and represent that cohomology class, and suppose it's not empty, Hitchin defined a functional on this space, gamma plus, to R plus by just integrating, by taking the total volume of the manifold with respect to that representing cohomology class. And he showed that the critical points of H are exactly the ones that satisfy that we're already assuming it's closed, that they satisfy that it's co-closed. So if you could prove the existence of a critical point in any given gamma plus, you'd prove the existence of a G2 metric. And in fact, the critical points are all local maxima. It's not hard to show. And so the natural thing to try is to look at the gradient flow of Hitchin's functional. That is, start with a phi and evolve it according to, move it in the direction of the Laplacian. Because if the Laplacian is 0 on a compact manifold, then of course that implies that phi is closed and co-closed. And if we start with a closed form, then the Laplacian is still closed. This evolution equation preserves the closure of phi. And if this thing could run towards, it's easy to show that this actually increases the volume of phi. So it's headed towards maxima if maxima exist. So it has all the, it has the desirable properties. And like I said, a fixed point, that is a thing for which the Laplacian is 0, is actually G phi parallel. And we know some basic things about it. The volume form is pointwise increasing, as I said. I and a student actually looked at, it's not completely obvious because it's invariant under the diffeomorphism group, that there's a short time existence for the flow, but a student of mine, Feng Shu, and I worked out that in fact short time existence does work in that case, but Jason Lotte and Wei actually went much further. They proved that this flow has Xi-type estimates, and you get existence of the flow unless the curvature blows up. So that's a good sign. And you can understand a lot about the solitons. That is, if you look at the phi for which, if you look at the phi and vector fields for which the Lie derivative with respect to phi, the Lie derivative of phi with respect to x is a combination of the Laplacian plus a multiple of phi, then those are the things for which the cohomology class phi, phi evolves by basically a multiple, right? And so up to a fixed multiple, it gives you, once you normalize, it gives you basically at a fixed point. That these things exist, sort of like the solitons in Riemannian geometry for the Ricci flow. These things exist, and they depend on, Cartan's techniques show that they depend on 16 functions of 6 variables. But there's a lot of things we don't know. We don't know how to tell when an orientable spinable manifold has a closed G2 structure. In fact, we don't even know whether or not it exists for S7, the simplest compact 7 manifold that we know. Can we find checkable conditions that would guarantee convergence of the flow so that it can be used to prove existence of new G2 holonomy metrics? In this particular, in the Riemannian case, the interesting solitons all are gradient solitons. That is, the vector field x is the gradient of a function. But and we know examples of such things, gradient solitons for this flow. We know examples, but unfortunately, Cartan's methods run aground in this. I'm not saying they fail, but they certainly get stuck at the limit of our computational ability, because it turns out that that the conditions for a gradient soliton is not. It's not involutive in Cartan's sense, and the standard method of trying to close it up to get an involutive system becomes so computationally complex after 2 steps that nobody's been able to actually push it beyond that. So we still don't know how many gradient solitons there are, in spite of the fact that most of the examples we actually know are gradient. But that's only a tiny, tiny sliver of the local examples that exist. And of course, the thing that makes in the Ricci flow case, the thing that makes things really interesting is understanding how singularities develop and how to move beyond the singularities. But we don't have a good understanding of the full singularity things that can show up in the G2 case. And in fact, the indications are that that lots of complicated things can happen, and so until we have a better understanding of that, I think this program is a little stuck. We need some more. We need better understanding of the singularities that can arise. In particular, the kinds of solitons and singular things that can happen. Let's see. I'm running out of time. Let's see. Very briefly, I'll say a little bit about this, and then I think I'll stop. Again, the analog with Kähler geometry is, in Kähler geometry, the thing that gives you a lot of interesting phenomena are looking at the submanifolds, the Kähler, the subvarieties, and of course also the special Lagrangian subvarieties which show up in the SUN case. And of course you have this whole geometry of holomorphic mappies and bundles. And so, in Calabi-Yau geometry, in addition to the complex submanifolds, there's also the special Lagrangian submanifolds and their foliations, and and these turn out to have lots of interesting phenomena that show up in physics and in mathematics, understanding the moduli space. And so the analog in dimension in G2 geometry is you have this parallel 3 form and its dual 4 form. It turns out that these forms are calibrations in the sense of Harvey and Lawson. That is, they pull back to any submanifold. For a 3-dimensional submanifold, phi pulls back to be at most a multiple of the volume form. And when it is the volume form on the submanifold, it's absolutely minimizing its homology class. And it turns out that there's lots of these submanifolds locally. There's every analytic surface in the 7-manifold that lies in a unique 3-manifold that's calibrated by phi, the so-called associative manifolds. Every analytic integral 3-manifold of phi, that is, if you have a 3-dimensional submanifold on which phi vanishes when you pull it back, it lies in a unique 4-manifold calibrated by star phi, the so-called co-associative submanifolds. And those existence results persist for any closed G2 structure that's real analytic in G-phi harmonic coordinates. So that gives you something to play with. But now the question of moduli for these things becomes quite complicated because there's no 3-manifolds like this in particular. Because it's an odd dimensional manifold, there's not a lot of characteristic classes that you can use to, or inequalities that can be used to give you dimension bounds or prove the existence of smooth things that aren't obstructed and so forth. So it actually takes a lot of work to begin to understand these things, and people will talk about that in the lectures. Actually, I feel like I'm running out of time, so rather than move on to the next thing, I think I'll stop here, because lots of people are going to talk about all these things, more recent developments in the following lectures. So, okay, thank you.